My name is Sudhakar, and I'm presenting my work called Uncertainty from Motion for DNN Monocular Depth Estimation. This work is in collaboration with my advisors, Vivian Z and Sirtash Karaman. There's been increasing interest in the task of monocular depth estimation, where we use a DNN to predict a depth value for every pixel in an RGB input image. Now, when we deploy this DNN to the real world, we don't have access to the actual error, and these errors can come from uncertainty about the data itself, such as dark or blurry images called aleatoric uncertainty, as well as uncertainty about inputs the DNN hasn't seen often, if at all, during training, called epistemic uncertainty. For example, there's high error around the fan and vacuum in this image, likely due to issues with lighting and cropping, resulting in aleatoric uncertainty, as well as there not being many examples of these objects in the training data set, resulting in epistemic uncertainty. Ideally, we can estimate both types of uncertainty well, so we can make safe decisions based on the DNN prediction. Unfortunately, methods to estimate epistemic uncertainty usually require multiple inferences per input, since they measure the disagreement or variance between networks to estimate uncertainty. This results in uncertainty estimation that is high quality, but too slow for real-time applications and too energy-intensive for resource-constrained scenarios. We propose uncertainty from motion, a new algorithm that enables close to state-of-the-art ensemble uncertainty quality while only requiring one inference per input. Uncertainty from motion, or UFM, accelerates not only ensembles, but also any method that requires multiple inferences per input, such as MC dropout and Bayesian neural network-based approaches. And UFM requires no retraining of the networks. The main insight of UFM is that there is temporal redundancy in video inputs, where we see the same points in 3D space from different views, as seen in these images. So instead of running M inferences per input, we can run one inference per input and merge temporally the predictions that are actually just multiple views of the same points in 3D space to get the total uncertainty estimate. We merge predictions temporally by projecting depth predictions out to 3D space and finding correspondences between images to find pixels in the current image that are actually additional views of points we have seen before in earlier images. We combine predictions that are multiple views of the same point in 3D space through a mixture of Gaussian's approach to obtain a total predictive uncertainty. We test UFM on both in-distribution and out-of-distribution sequences to test how well it can capture ensemble uncertainty quality. And we see by comparing the negative log likelihood, or NLL, and the expected calibration error, or ECE, of ensemble uncertainty from motion and the baseline ensemble, that uncertainty from motion is able to produce similar uncertainty quality to that of the state-of-the-art, all at a fraction of the latency and energy cost. And this is because we only need to run one inference per input. The key takeaways of this work is that number one, we can obtain high-quality uncertainty estimates while still only running one inference per input through a new algorithm called uncertainty from motion. And number two, UFM is really able to get this efficiency boost because there is so much temporal redundancy in video inputs, allowing us to merge the uncertainty estimates temporally.